This is Chapter 8a, Introduction to Confidence Intervals. We're going to start off by touching on what the core piece of a confidence interval is, and that is a point estimate. Point estimate is a single value used to approximate a parameter. It's a very important definition. You need to be able to understand what I mean when I use the phrase point estimate. I mean just this. It's just a value used to approximate a parameter. Now, we will then oftentimes add the adjective best point estimate to say which is the one that we want to use. What I mean by that is that a point estimate is just a value used to approximate a parameter. I could approximate anything I want, but the best point estimate is going to be the best value to use to approximate said parameter. And so we're going to say that the sample proportion p hat is the best point estimate of the population proportion p. And hopefully that makes sense to you. It's this idea that if I don't know what the true population proportion is and I had to guess at what it is, point estimate is just my best guess, right? Then I would take the sample proportion p hat. If I were to say I don't know how good of a free throw shooter I am in truth, that being the population proportion, if I go out and I shoot 20 free throws, take the sample proportion of however many I make in those 20 and say that's my best guess as to my true skill level. Is it perfectly accurate? No, it's just my best guess at it. I do have a note here that sometimes we report the population proportion as pi. I will not do that. Your textbook will not do that. However, depending on what sort of alternate resources you find out there, sometimes they will call the population proportion pi instead of p. That kind of should make sense to you because for parameters, we tend to use Greek letters, right? Sigma is the population standard deviation, mu is the population mean. However, the reason we don't use pi in this course to designate the population proportion is because while pi is the Greek letter for p, pi has a different meaning in math. And so we don't want to confuse you by throwing a pi around because then you might say, wait a minute, I already know what pi is. Now there's the symbol pi that means something else that might get confusing. So instead, this is the one case where we're going to have a parameter that is not notated by a Greek letter, but the parameter is going to be p. And then we can also do the same thing with means. The sample mean x bar is the best point estimate of the population mean, mu. And so we're just starting off by saying we're going to have a point estimate because the whole point of this course, I don't know a parameter. And so what do? I take a sample and I use that sample to make an inference about this parameter. And so what we're saying here is that when I don't know p, I'm going to take a sample and the p hat that I get from that's my best guess as to what p really is. When I don't know mu, I'm going to take a sample and the x bar I get from that's going to be my best guess at mu. Now, this chapter, the whole purpose of this chapter is to say that's all well and good. Like we could stop right here. We could stop and say we've met our objective of I don't know what the truth is, so I take a sample and boom, now I've got my best estimate. But the problem is the follow-up to that would be how good of an estimate is it? It's the best, but how good? What might I be off by, that sort of thing? And that's what this whole chapter is about, is we're going to dive deeper down the rabbit hole and say, yes, p hat is the best point estimate for p, x bar is the best point estimate for mu. However, I need to understand how good of an estimate that may be. And that's what the rest of the chapter talks about. And so how are we going to do that? We're going to do that by a confidence interval. A confidence interval is defined as a range or interval of values used to estimate the true value of a parameter. Now, what we need to understand about a confidence interval is that it's a set of values that I think contain the truth. Notice I said the same words right there. You're going to have a lower bound, you're going to have an upper bound, and you're going to say somewhere in between there is where I think the true parameter lies. It's this idea that we just talked about, that I don't know what p is. What's my best guess? My best guess is p hat. I don't know what mu is. What's my best guess? My best guess is x bar. But if I want to say, yeah, that's the single point I think, that's one thing, but a confidence interval is going to allow me to say further, I think that this unknown value of P or this unknown value of mu falls between blank and blank. And that's what a confidence interval is. So we're going to quickly introduce another symbol. That's for significance level. It's the symbol alpha. It's the Greek letter, introduces their alphabet. And what the significance level is not relevant for us for this chapter. It does have a meaning. We could dive down that rabbit hole, but I'm going to choose not to. We will come back to this a little bit more in chapter 9 after your next exam. But for now, just know that when we use the Greek letter alpha or the phrase significance level, we mean the same thing. Those are interchangeable terms. And this is going to be utilized because the confidence level is a probability 1 minus alpha. And of course, I note here that we often express this as a percentage. So our confidence level will typically be 80%, 90%, 99%, 95%. And so if I have 95% confidence, that means my significance level is 0.05. If I have 90% confidence, that means my significance level is 0.1. If I have 80% confidence, my significance level is 0.2, right? We should be able to go back and forth from that pretty easily because they are complements. And the confidence level is the probability that after repeated sampling, the confidence interval contains the parameter of interest. Okay, that's an idea that might seem a little bit weird, this repeated sampling. We've kind of touched on this previously. It gets into the idea of a sampling distribution. And if you recall, when we talked about sampling distributions, we said we never actually would go out and get a bunch of X bars and build up a distribution. We never would actually go out and get a bunch of P hats and build up a distribution. And that's true. That was a theoretical idea, something that we said we just needed to know what it would look like in theory so I could know how my X bar looked and how my P hat looked compared to the theoretical what would everything else look like. And that's the same idea here. We're talking about this repeated sampling idea that is just a theoretical thing. We're not actually going to go do it. And the confidence level is the probability that if we were to do that, the confidence interval would contain the parameter of interest. Again, we're not actually going to do this repeated sampling. We're just saying that a confidence level is a probability that if we were to do that, we know how many times we would actually capture the parameter of interest. Why is that important? That's important because when I say my confidence interval is from blank to blank, let me put some numbers to that just to, hammer it home for us. If we're talking about a proportion, we know that a proportion can only go from 0 to 1. So if I were to say that my confidence interval on a proportion went from 30% to 60%, okay? By definition, we think that the true value of P falls between 30% and 60%, but how sure are you? The confidence level answers the question, how sure are you? But it specifically answers the question in this way of saying, if we were to do this a bunch of times, that percentage of the time, this interval would actually capture it. It's this idea of hypothetically, again, we're just off in this theoretical land when we talk about repeated sampling. In theory, if we were to go do the same thing 100 times and get 100 different intervals, a 95% confidence interval says 95 times out of 100, we actually would capture the parameter of interest. And that interval of 30% to 60%, that'd be right. It would be somewhere in between there. I don't know where in there, but it would be somewhere in between there in that 30 to 60, 95% of the time. 5% of the time, I'd be wrong, right? And that's kind of a risk we take, but we're saying most of the time we think this concept works.